A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
You know, Herman, I was looking at some telemetry from the latest Starlink launch yesterday, and it hit me how much we still treat satellites like mirrors in the sky. We send a signal up, it bounces off a piece of hardware, and it comes right back down. It is basically a very expensive game of orbital catch. We have these multi-billion-dollar constellations, but for the most part, they are just acting as transparent relays. They don't know what they are carrying, they just reflect it.
Herman Poppleberry here, and you are hitting on the fundamental limitation of what we call the bent pipe model. For decades, that was the only way to do it, because the computational overhead of doing anything else was just too high for a space-hardened processor. If you wanted to do actual packet switching in orbit, you needed a level of radiation-hardened compute that simply didn't exist at a reasonable power envelope. But Daniel's prompt today really pushes us past that era. He is asking about the feasibility of a true space-based internet architecture, moving from those simple relays to decentralized, autonomous nodes with things like edge caching and a dedicated version of the Border Gateway Protocol. We're talking about turning the vacuum of space into a giant, high-speed distributed data center.
It is a massive shift. Today's prompt from Daniel is about whether we can actually build a network in the stars that looks and acts like the fiber backbone we have on the ground, but with the added complexity of every single router moving at 17,000 miles per hour. Daniel wants to know if we can use high-orbit satellites to talk to low-Earth orbit constellations to kill latency once and for all. It is a vision of a tiered internet where the physical location of the server matters less than the orbital plane it is currently occupying.
The physics of this are actually on our side for once, which is rare in aerospace. Most people assume satellite internet is naturally slow because they grew up with those old geostationary dishes that had a 500 millisecond round trip time. But as we have talked about before, specifically back in episode 535, when we looked at the differences between geostationary and low Earth orbit, the distance is the only real enemy there. When you move the nodes closer, to around 550 kilometers, the math changes entirely. In a bent pipe model, you are still tethered to a ground station. You go up to the satellite, back down to a gateway, into the terrestrial fiber, and then back up. It is that back down and back up part that kills your performance.
But Daniel is suggesting a hybrid, using the wide coverage of a geostationary satellite as a sort of command and control layer that feeds data down to the low Earth orbit mesh. Does that actually work? Or are we just adding more hops and increasing the lag? It feels like trying to coordinate a swarm of bees from a mountaintop.
The relay model Daniel is describing is essentially a tiered architecture. Think of the geostationary satellites as the long-haul backbone and the low Earth orbit satellites as the local edge nodes. The feasibility depends entirely on the inter-satellite links, or ISLs. If you are using traditional radio frequency links, you are limited by bandwidth and interference. You also have the problem of beam steering and the massive power required to punch a signal through the atmosphere or across thousands of miles of vacuum. But the industry has moved toward optical laser terminals. This is the game changer.
I remember reading about the Starlink Gen 2 performance metrics. They are seeing nearly zero packet loss on those laser links now. But here's the thing that always trips me up. If I am in New York and I want to send a packet to London, why would I ever want that packet to go up to a satellite, then across to another satellite, and then down? Is fiber not just fundamentally better because it is a physical wire? We have spent trillions of dollars burying glass in the ground.
This is where the physics gets fun. Corn. The speed of light in a vacuum is approximately 300,000 kilometers per second. But in a standard fiber optic cable, light travels through a glass core. That glass has a refractive index that slows the light down by about 30%. So, light in a vacuum is actually 47% faster than light in a fiber optic cable. When you are talking about transcontinental distances, that 47% is the difference between winning and losing in the modern economy.
Wait, 47%? That is not a marginal gain. That is not like upgrading from 4G to 5G. That is a massive structural advantage for space. You are saying that even with the extra distance of going up to 500 kilometers and back down, the vacuum speed makes it faster than a straight line through the Earth's crust.
It is the reason high-frequency traders are so obsessed with this. If you are routing a signal from London to Singapore, a straight line through the vacuum of space is significantly faster than following the curvature of the Earth through thousands of miles of glass cable, even with the extra distance of going up to orbit and back. The vacuum is the ultimate low-latency medium. But to unlock that, you can't go back down to the ground until you reach the destination. You have to stay in the mesh. You have to hop from satellite to satellite using those lasers.
So the bottleneck isn't the vacuum, it is the routing. On the ground, we have the Border Gateway Protocol, or BGP, which basically tells the internet how to get a packet from point A to point B. It is the map of the internet. But on Earth, the routers stay put. They have an IP address, they're in a rack in a building, and they don't move. In Daniel's vision of a space-based internet, your routers are screaming across the sky at 7.5 kilometers per second. How do you maintain a routing table when the topology of your network changes every few seconds?
You have identified the core engineering hurdle for what we are calling Space-BGP. In a terrestrial network, if a router moves, it is usually because a backhoe hit a cable or a data center lost power. It is an exception. In low Earth orbit, movement is the constant. As of today, March 21st, 26, we have over 12,000 active satellites in low Earth orbit. Each one of those is a node that is only visible to its neighbors for a few minutes at a time. If you use standard BGP, the network would spend all its time flapping, constantly announcing that routes have disappeared and reappeared.
So the standard BGP would just have a total meltdown. It would spend all its time updating the table and zero time actually moving data. It would be like trying to use a paper map of a city where the streets are constantly rearranging themselves.
The January 26 draft standards from the International Telecommunication Union, the ITU, actually proposed a predictive routing model for space. BGP. Unlike terrestrial BGP, which is reactive, meaning it waits for a failure to find a new path. Space. BGP can be deterministic. We know exactly where every satellite will be at any given microsecond because orbital mechanics are predictable. You don't have to wait for a node to tell you it is leaving. You already have its orbital elements in your local database. The routing table isn't a static list, it is a four-dimensional function of time.
That is an interesting twist. The very thing that makes it hard. The high velocity is also the thing that makes it predictable. You aren't guessing where the next hop is, you are calculating it. But what about the handoff? If I am a satellite over the Atlantic, and I am passing a terabyte of data to a satellite coming up over the horizon, that laser has to lock on with incredible precision, while both of us are moving at 7.5 kilometers per second. That sounds like a nightmare for the pointing, acquisition, and tracking systems.
The pointing accuracy required is like trying to hit a moving quarter with a laser pointer from several hundred miles away. But the newest optical terminals are using fast steering mirrors and automated acquisition sequences that can lock on in less than a second. Once that link is established, you have a 10 gigabit or even a 100 gigabit per second pipe that is completely immune to radio frequency interference. And because there is no atmosphere in the way between satellites, you don't get the scintillation or signal degradation you would get on a ground-to-space link.
Let's talk about the other part of Daniel's prompt, edge caching. On the ground, we use companies like Cloudflare or Akamai to store copies of websites closer to the users so they load faster. Does it actually make sense to store data on a satellite? It seems like a lot of weight and power for a hard drive in space. Plus, the satellite is moving, so it is only close to a user for a few minutes. Doesn't that defeat the purpose of a content delivery network?
It makes a lot of sense when you consider the backhaul problem. Right now, if a satellite takes a high-resolution image of a farm in Iowa, it usually has to wait until it passes over a ground station to dump that data. That creates a massive lag between data acquisition and data utility. If you have orbital edge caching, that satellite can process the image locally using a space-hardened AI chip, identify the relevant parts, and then cache that data in the mesh. The edge isn't a fixed location on the ground. It is the shell of satellites surrounding the planet.
So if a researcher in Israel wants to see that data, they don't have to wait for the satellite to talk to a ground station in the US, and then wait for the US ground station to send it over undersea cables. They can just pull it from the nearest orbital node that has it cached. The data stays in space until the very last mile.
The orbital mesh becomes a decentralized content delivery network. We are moving toward a model where space is not just a pipe, but a compute layer. This is what people are calling space as a service. You are not just buying bandwidth, you are buying orbital compute cycles and storage. Imagine a world where the heavy lifting of weather modeling or climate tracking happens entirely in orbit, and only the final results are beamed down to Earth. It saves an incredible amount of downlink bandwidth, which is the most expensive part of the whole system.
I can see the appeal, especially for something like Earth observation or weather tracking. But what about the security? If we are building a decentralized internet in space, how do we stop someone from launching a rogue satellite and performing an orbital man-in-the-middle attack? If they can join the Space-BGP mesh, they could theoretically intercept or spoof data. On the ground, we have physical security for our data centers. In space, anyone with a rocket can get close to your hardware.
That is a legitimate concern, and it is why the security protocols for these inter-satellite links are being built on zero-trust architectures from the ground up. Every node has to have a cryptographically verifiable identity tied to its hardware. In episode 12 and 71, we talked about how physical fiber cables are the first casualty in modern high-intensity conflicts. A space-based mesh is actually more resilient in some ways because you can't just cut a cable. You would have to physically take out multiple nodes or use sophisticated electronic warfare to disrupt the laser links. And because lasers are highly directional, jamming them is significantly harder than jamming a radio signal.
And if you take out a node, the Space-BGP just routes around the whole. It is the ultimate self-healing network. But I wonder about the political side of this. If the US and Israel and our allies build this high-speed orbital backbone, does it create a new kind of digital divide? If you're a country that isn't part of the mesh, are you basically stuck in the slow lane of the old terrestrial internet?
There is a definite geopolitical race happening right now. We are seeing a push for a Western-led orbital standard that prioritizes open protocols and encryption versus other blocs that want more centralized control over satellite traffic. The beauty of the model Daniel is asking about is that it is inherently difficult to censor. If your internet is coming from a mesh of 12,000 satellites moving overhead, a local government can't just flip a switch at a central exchange to shut it down. It challenges the very idea of a national internet.
It is the ultimate end run around the great firewall models. But let's look at the practical side for a second. If I am an aerospace engineer today, or a software developer, what does this mean for me? It sounds like the line between a network engineer and a rocket scientist is getting very blurry. We are moving from how do we keep the satellite in orbit to how do we manage a distributed database across 10,000 moving nodes.
Software-defined networking, or SDN, is becoming the most critical skill set in the industry. We are seeing a huge demand for people who understand how to write code for high latency, high mobility environments. If you are interested in this, you should look into some of the open source space networking simulation tools that are popping up on places like GitHub. Tools like the Orbital NS3 project allow you to simulate these orbital topologies and test how different routing algorithms handle node failures or high congestion. You can actually see how the 47% speed advantage of the vacuum plays out in a simulated global network.
I love the idea that the future of the internet might be more about orbital mechanics than digging trenches for fiber. But let's go back to the relay model. Daniel mentioned passing data from geostationary down to low Earth orbit. Is that actually happening yet, or is it still theoretical? It seems like the distance between a geostationary satellite at 35,000 kilometers and a low Earth orbit satellite at 500 kilometers is still a huge gap to bridge with a laser.
It is happening in specialized military and government applications first. The U.S. Space Force and the Israeli Ministry of Defense have been experimenting with these multi-orbit architectures for a while. We touched on some of the Israeli innovations in space-based AI and laser comms back in episode 432. The goal there is to have the geostationary satellites act as a persistent eye in the sky that can task the low Earth orbit satellites in real time. The geostationary satellite has the big picture, and it uses that high altitude vantage point to route commands down to the LEO constellation, which has the low latency connection to the ground.
So the geostationary satellite sees something interesting, sends a command down to the nearest low Earth orbit node to take a closer look, and that node then routes the data back through the mesh to the user. It is a very elegant way to use the strengths of both orbits, the wide area view of the high orbit and the low latency, high resolution capability of the low orbit. But Herman, what about the power? These lasers and high-speed routers must be absolute power hogs.
The challenge is the power budget. Laser terminals and high-speed routers require a lot of juice. When you are on a satellite, your power is limited by the size of your solar panels and the efficiency of your batteries. Every watt you spend on a routing table update is a watt you aren't spending on your primary sensor or your propulsion system. This is why we are seeing a move toward more efficient, specialized ASIC chips designed specifically for orbital routing. You can't just throw a standard server rack into a satellite.
Right, because of the radiation. You mentioned that earlier. The radiation in space will flip bits in your memory and fry your processor in weeks if it isn't properly shielded. So you are building a data center that has to be radiation hardened, power efficient, and capable of operating in a vacuum where heat dissipation is a nightmare because you can't use fans.
You have to use passive cooling and heat pipes to move thermal energy to radiators. And shielding adds weight, and weight adds cost. It is a constant trade-off. But the shift towards smaller, mass-produced satellite buses is bringing the cost down. We are moving away from the era of the billion-dollar bus-sized satellite that has to last 20 years toward constellations of smaller satellites that we replace every 5 years. That allows us to iterate on the hardware much faster. We are effectively bringing the move fast and break things ethos of Silicon Valley to orbital mechanics.
It is essentially the Moore's law of space. If we can upgrade the routers in the sky every 5 years instead of every 20, the space-based internet will catch up to terrestrial speeds much faster than people realize. I think the takeaway here is that the bent pipe is a relic. The future is a smart, autonomous, and highly mobile mesh. We are building a shell of silicon around the planet.
The implications for global connectivity are staggering. We are talking about a world where a person in a remote village in Africa or a research station in Antarctica has the same sub-millisecond access to the world's data as someone sitting in a data center in Northern Virginia. The vacuum of space is going to be the backbone of the next billion people coming online. It democratizes access to information in a way that physical cables never could, because cables require permission from every country they pass through. Space is different.
It is a wild thought. The internet started as a way to connect a few universities with physical wires, and it might end up as a global shell of lasers and silicon. Herman, you've been surprisingly restrained on the technical jargon today. I expected you to start reciting ITU packet header specifications for the new Space-BGP draft.
Give me time, Korn. We still have a few minutes left. I could go into the specifics of the Doppler shift compensation required for optical links between satellites in different orbital planes. When two satellites are moving toward each other at combined speeds of 15 kilometers per second, the frequency of the laser light shifts significantly. If you don't account for that, your receiver won't even see the signal. It is like trying to listen to a radio station where the frequency is constantly sliding up and down the dial.
See, there it is. I knew the Pubbleberry intensity was simmering under the surface, but that actually brings up a good point about the complexity. This isn't just about plugging in a router. It is about real-time relativistic corrections and high-precision physics. You are basically running a global telecommunications network on top of a physics experiment.
It is the ultimate engineering challenge. You are building a global computer where every component is falling around the Earth at incredible speeds, and you have to make it feel as stable as a cable plugged into your wall. The January draft from the ITU is just the beginning. We are going to see a lot of debate over how much autonomy these satellites should have. Do we want them making their own routing decisions based on local congestion, or do we want a centralized brain on the ground telling them what to do?
I will bet on decentralization every time. It is the only way to handle the scale. If you have 12,000 nodes, you can't wait for a ground station in Nebraska to tell a satellite over the Indian Ocean how to route a packet. It has to be autonomous. Well, this has been a fascinating deep dive. Daniel always brings the good stuff. He's really forced us to look at the where and how of the next generation of the web.
He really does. It is great to see him applying that technical background to these kinds of structural questions. It is exactly what this show is about, taking a weird prompt and finding the hard engineering reality underneath it. If listeners want to dive deeper into how we actually manage the tasks for these satellites, they should definitely check out episode 1430. We went into the orbital myth and how satellite tasking actually works on a technical level. It complements this discussion on the networking side perfectly.
So, what is the final verdict, Herman? Is the space internet just a backup for when the undersea cables get cut, or is it the future primary backbone? Are we going to stop digging trenches for fiber altogether?
I think it starts as a high-value niche for things like high-frequency trading and military comms, but as the scale of the constellations grows, the cost per bit will drop to the point where it becomes a legitimate competitor to terrestrial fiber for long-haul traffic. The 47% speed advantage in a vacuum is a physical reality you just can't beat on Earth. You can't make light go faster through glass. Space is the only way to win the latency war.
It is the ultimate unfair advantage. I can't wait to see how the Space-BGP standards evolve over the next year. It feels like we are writing the constitution of the orbital internet right now. We are moving from the era of, can we do it, to how do we govern it?
And that is a much more complex question. But for today, I think we've covered the technical feasibility. The answer to Daniel's prompt is a resounding yes. It is not only feasible, it is already being built.
We should probably wrap this up before you start explaining the refractive index of different types of space-hardened glass, or the thermal conductivity of satellite radiators.
I will save that for the next time we talk about orbital telescopes. There is some fascinating work being done on liquid mirrors in zero-G, but that is a conversation for another day.
Looking forward to it. Thanks as always to our producer Hilbert Flumingtop for keeping the gears turning behind the scenes. And a big thanks to Modal for providing the GPU credits that power the research and generation of this show. We couldn't do these deep dives into orbital mechanics and networking protocols without that kind of compute.
This has been My Weird Prompts. If you are finding these technical breakdowns useful, a quick review on your podcast app of choice really helps us grow the show and reach more people who are interested in the intersection of space and technology. It helps the algorithm find us, which is its own kind of complex routing problem.
You can also find us at myweirdprompts.com for our full archive and all the links we mentioned today, including the ITU draft standards and the open source simulation tools. We will be back soon with another prompt from Daniel.
See you then.
Goodbye, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the flows from slow